We will start our discussions today from considering an electron which is being generated from a heated filament maybe tungsten from thermal emission, and after it has been generated, these electrons they have been accelerated by a potential of say 50,000 volts, and after they have been accelerated, they come into the effect of two magnetic lenses and after passing through these magnetic lenses, they are allowed to strike a specimen and produce a diffraction pattern. So this strike the specimen, and then they cause diffraction. Diffraction pattern, and it is found on a photographic plate. Now, the wavelength associated with electrons accelerated by such potential and say we are talking about 50,000 volts. So lambda is equal to h by mv, and that comes around equal to 0.0536 angstrom, and this value is about 1/10 of that of an X-ray. So what we can imply from this observation is, although Bragg's law that is 2 raised ampere is equal to n lambda, although Bragg's law holds for electron diffraction as well, the diffraction angle is very much smaller than that in the case of X-rays. But the difference is the diffraction angle is much smaller than X-rays. Now, another characteristics of an electron beam is the ease with which it is absorbed. In electron beam, we're talking about the ease with which it is absorbed. Now, just the entire for electron diffraction to take place, the entire diffraction apparatus should be operated in a good vacuum, and the transmission of specimens can be only in a millionth of an inch in thickness. So these two are very vital conditions for electron diffraction. Now, this the use of very thin specimen, this can be avoided if we have reflection specimen. Can avoid this problem of lower thickness. Now, if the electron beam is caused to graze the surface, only graze the surface, so the diffraction pattern produced is only that of the surface, that is about 100 atoms. Deep. So the diffraction pattern only characterizing these 100 atoms on the surface. So that is why this is feature of electron beam is useful in determining the surface films, that as those formed in corrosions and all. Apart from this electron diffraction, there is another way of investigating material, that is called the neutron diffraction. And so for neutron diffraction, we first were at the source of neutrons. So for that we require a nuclear reactor. Now these neutrons they come from as in the form of radiations. And these radiations, they contain many wavelengths. Now we need to have the characteristic radiation for our purpose, and so we get reflection from our monochromator. and that often happens to be a single crystal of lead. Now, the intensity of the initial neutron beam is reduced by a factor of intensity. It gets reduced by a factor of 10 to the power 3 by this operation, that is getting reflected from a monochromator. And by further diffraction by the sample, the band beam is quite weak, and on further diffraction, the final beam is quite weak. Now, the advantages that we get in the neutron diffraction, apart from an X-ray diffraction or the electron diffraction, comes from the source of diffraction. To look into that matter, if we consider that the nucleus from where these neutrons are produced are the source of these neutrons, where the electrons are primarily responsible for diffraction of X-rays and electron beams. Now, the number of electrons increases uniformly with atomic number. So, if we increase atomic number, so the number of electrons in an atom, they would also increase uniformly, and so the diffraction power of the atoms for X-rays and electron exhibit a similar increase. That means for light elements like hydrogen and carbon have lower diffraction power compared to heavy elements. So these are supposed to have low diffraction power compared to higher heavier elements. So that is why it is difficult to study metal structures, such as if someone like to study a metal hydride. Then, since the diffraction power is lower in this case, so it is difficult to study. So because they are containing both heavy, this is a heavy and this is a light. So in that case, the X-ray and electron diffraction are not able to get a proper information of what is happening, since lower atomic number elements have low diffraction power. This is one of the problems. Second problem is studying atoms whose atomic numbers are nearly the same. For example, if we would like to have iron and cobalt, so these have a similar atomic number. So that is why, so Z is close. The atomic number is close, so it would imply that these have identical scattering power. So for X-rays matter, so distinguishable, we cannot able to distinguish between an error and cobalt. And it is also difficult to determine by X-rays the position of in the crystal structure occupied by each kind. So it is difficult. For X-ray to determine the position of atoms of each kind, that means iron and cobalt. Now, these two problems are overcome in case of a neutron diffraction, and because in a neutron diffraction, so the various elements show a random distribution of neutron scattering power. So a random distribution of neutron scattering power so to plot we take the different elements, we compare the scattering power of say so we have the elements here. So we talk about hydrogen, deuterium, beryllium, carbon, magnesium, aluminum, titanium, iron, cobalt, molybdenum and tungsten, and then we compare the scattering power of an X-ray of a neutron and of an X-ray. So the neutron scattering powers are as follows for the case of abilities. Neutron and for the X-ray. The scattering powers for an hydrogen atom are as follows. They are 1.8, then for the deuterium it is 5.4, then for beryllium it is 7.7, for carbon it is again 5.4, and for magnesium it is 3.6, for aluminum it is 1.5, for titanium it is 1.8, for iron it is 11.4. For cobalt it is 1.0, and for molybdenum it is 5.5, and for tungsten it is 2.7, and in the case of X-rays it is 1, 1, 4, 6, 12, 13, 22, 26, 27, 42, and 74. So they have been, the elements are arranged in an increasing order of atomic number. So you can see the X-ray scattering power increases accordingly. Now, what the advantage that we get? The first advantage you can see is, as previously told, you can distinguish between these two. So you can see that although these have the similar scattering powers in X-rays, they have a huge difference in scattering power in case of neutrons. So you can distinguish between these two types of elements. And interesting is that the light elements like hydrogen, then beryllium, the neutron diffraction powers are similar in the case, similar to the, there is not much of a difference, like in this case it is 1 and there is 74. So whereas not that much of a difference in neutron power. It varies from 1.8 and the maximum went around 7.7, and all the values are close. So actually you can use this neutron diffraction power if there is a combination of a metal, of a heavier and a lighter element, like in the case of a metal hydride. So these are the two advantages we have found in the case of neutron diffraction.